Hello learners, welcome to Let's Code. So in the previous lecture, we have understood number system, base, power, and how to convert any number system into decimal using a formula. Now it's time to talk about the most important number of all. In computer programming, what is the most important number system? Binary, right? So let's discuss binary today. So why is binary important? Because computers understand only binary languages. Why? Because unlike human beings, computer do not have 10 fingers to count 10 numbers, right? At the lowest level, computer understands only two states, on or off. That's it. Okay. There is no third state and no maybe. So, like in human language, you can say, did you solve this problem? You can say, yes, I solved it. No, I did not. Maybe I solved it partially. So such things does not exist in computer. There is either true or false. There is no any other state. That is why computer uses base 2 and that is called binary number. Why? Because it can only have two states, either on or off state. Okay, so let's write down the two states. So computer understands only two states. What are those? Either on state, that means 1, or off state, that means 0. On is also called true and off is also called false. So that is why we need to learn binary because computer only understand these two states, on or off. Now, in the previous lecture, we have already discussed conversion of any binary number into decimal. So we discussed one example, like let's say there is given one binary number. So in order to convert this number into decimal, we use the formula of symbol into base to the power positional value, like this, right? Symbol into base to the power positional value for all of the symbols and then sum those, right? So let's write it down once again. 2 to the power 1 plus 1 into 2 to the power 0. And that turns out to be 11 in decimal number. So here also it's the same logic, same formula, only the base is different, right? So why so many number system exist? That is because binary exists because hardware at hardware level it can understand only two language. Octal exists because it is also an compact binary representation. Why decimal exists? Because it is more human friendly. Why hexadecimal exists? This is used for memory addresses. So, so different number system exist for convenience, not complexity. So once we understand representation, we can start playing with bits. Now, let's talk why binary is so important. So everything inside computer is a binary. Every single thing which human read like numbers, characters, images, audio, video, texts, files, internet data, whatever we see in a screen, everything is binary. Even this YouTube video which you are watching is a very long sequence of zeros and ones. So that is why every programmers must learn binary. We write the code in high level language, but machine understands only binary. Memory works in binary, CPU operations are binary, bit manipulation is binary, performance optimization depends on binary only. So if you don't understand binary, we are working with machine blindly. That is why we must understand binary numbers. So now you can ask, if computer understands binary, and human thinks in decimal, what connects the two? How does the computer understand the human understood decimal language or any other data? The answer is very simple, by conversion. Anything we write on the screen in decimal number, it is internally gets converted into binary, right? So what is the method to convert any decimal number into binary? Let's learn about that. Okay. Conversion of a decimal number into binary. So the method of converting any decimal number into binary is very simple. We divide the decimal number repeatedly by 2, write the remainder, and again divide the quotient by 2. Again write the remainder, again divide the quotient by 2. So we do this step repeatedly until we have 0 as the quotient. For an example, we have to convert decimal number 13 into binary. So how we do that? We will divide this number by 2. So what is the quotient? 6. And what's the remainder here? So 13 remainder 2 is 1. Right. So next we have 6. So we again divide this 6 by 2. What's the quotient here? 3. And what's the remainder of 6 when we divide by 2? 0. Again we have to divide the 3 by 2. So what's the quotient? 1. And what's the remainder? It's 1. Now what do you have the as quotient? It's 1. Again divide by 2. So what's the quotient here? 0. And what's the remainder? So 1 remainder 2 is 1. Now once we have reached the quotient as 0, we do not need to further divide it. Right. So once we have done this step, we will just write the remainder in from the bottom to top. So from bottom to top, what's the value? It's 1, 1, 0, 1. Right? So this is how we convert any decimal number into binary using the repeated division by 2 and writing out the remainder. Let's quickly verify whether this is correct or not. So if we try to again write it in expanded form, it's 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. So that sums up 8 plus 4 plus 0 plus 1, that becomes 13, right? So this is how we convert any decimal number into binary and any binary number into decimal. We have learned both the approach. Just for better understanding, so let's try to convert one more decimal number into binary. Okay, so convert 18, 18 into, sorry, convert 18 into binary. So we once again we will apply the same approach here. We will divide 18 by 2. So the quotient will be 9 and the remainder will be 0. Again, divide 9 by 2, quotient will be 4 and remainder will be 1. Divide 4 by 2, quotient will be 2 and remainder will be 0. And again, we divide 2 by 2, quotient will be 1 and remainder will be 0. Once again, 1 divided by 2, the quotient is 0 and remainder is 1. So this is 1, 0, 0, 1, 0. This is what the corresponding binary number of 18. I hope you understood this conversion. So binary actually isn't hard. We do not deal with binary numbers in our day-to-day life. That is why it looks difficult than decimal number. Once you practice few conversion, it becomes very easy. Now let's talk about binary addition. So how should we add two binary numbers? Binary addition. So when you are asked how should we add two binary numbers, one can think like, let's convert the binary number into decimal, sum those decimal number, and then convert it back, right? Is this simple enough? Instead of making it simpler, optimized, we are making it much difficult for computer, because then computer will have to do the conversion and then add it and then again represent in binary number. This is way too lengthy and not optimal at all. That is why we will not follow that approach. We will directly learn binary numbers. And that is exactly same how we do decimal numbers. So what do we do when we have to add two decimal numbers? Let's say if we have to add 48 plus 56 in decimal number, what do we do? We just sum from left side. So 8 plus 6 is 13. We write 3 and we carry the 1 towards the left side. Why? Because 13 cannot be written in the 10 symbols which decimal base has, right? That's why we carry the extra part to the left side. Once again, we write it like 5 plus 4, 9, 9 and 1, 10. So since there is nothing more to carry toward left, we'll just write the carry as a new symbol left to the result here. So this is how we do the addition in decimal. So can we try to follow the same approach for binary as well? The same approach, but instead of writing in decimal, we will write in binary. So let's say if we have to sum, so let's say all the numbers here 1, 1, 1, 1, and let's say 1, 0, 1, 1. Now what will happen here? So 1, 1, that become, so what will happen? 1 plus 1, it will become 2. So since binary cannot hold 2, what we'll do here? We will write 0 and we'll carry the 1 toward left. Now what we have here? 1 plus 1 plus 1. So it's become 3, right? So what's the binary representation of 3? First of all, when we did 1 plus 1 equal to 0 and carried 1, what does this mean? The representation of 2 is 1, 0, right? That is why we write this part here and we carried the left part toward left side. Now when we have 1, 1, 1, what is this? This is 3. So what is the binary representation of 3? It's 1, 1. So what we will write here? We will write the right part here and we will carry the left part toward left. So here, once again, what do we have here? 1, 1, 0, which is 2. Again, this same. What we will write here? We will write the 0 here and we will carry the 1 toward left. Again, what is it? 1, 1, 1, which is this thing. What did we write here? 1 and carry the 1 Now, there is nothing here. So basically, nothing here means we can assume that there is 0. So we can just, so 0, 0, 1. What is it? 1. So we'll just write the 1 here. So this is how binary or addition happens. So if we have to write this thing, like how do you write in English? So we can write like this. Summation equal to digit 1 plus digit 2 plus carry. In each step, we are doing the same. We are summing the 2 digits and also the carry. Since there was no carry, we did not sum it. Since there was no carry, we did not sum it. So whenever there is carry, we have to sum that thing also. Now, how do we get the carry and what do we write here? So the result which we write is, it's nothing but the remainder of this number. So when we sum this, whatever the remainder comes up, we write the remainder here and we carry the quotient to the next part. So what do we did? What do we do? We write the remainder in place, and what do we carry? We carry the quotient part. Very similar to what we did when we converted. So what did we do when we convert any decimal to binary? We just wrote the remainder right, and we again did the repeated division for the all the quotients. So similarly here also, when we have to write as the result, we only wrote the remainder and the quotient part we carried. So that's exactly what we are going to do for all the binary summations. All right. So let's try to apply this logic once more with one more example. So let's say we are given binary number 1110, and we are given 1111. We have to sum this. So now let's understand from this terminology part. So summation is digit 1, digit 2 plus carry. What's carry here? There is no carry, right? So we can assume the carry is 0. Now what do we have in the result? Result is summation, which is digit 1 plus digit 2 plus carry, which is 1 plus 0 plus 0, which is 1 itself. Summation remainder 2. So if we do remainder of 1 by 2, what will the remainder? 1 only, right? So we write the remainder here. Now what is the quotient? So what is 1 by 2? 0, right? So we carried the 0 here again. Now again we do the same thing. Sum equal to digit 1 plus digit 2 plus carry. Again there is carry 0. We will sum 1 plus 1 2 and 0. It's 2 only. So what we will write here? Summation remainder 2. So 2 remainder 2 is nothing but 0. Right? 2 remainder 2. What is the remainder when you divide 2? What is the remainder? 0, right? So we'll write 0. And what is the carry? It's the question. So 2 divided by 2 is 1. So we will carry the question to our left. Once again, with the same sum 1, 2, 3. So what's 3 remainder 2? 3 remainder 2 is 1. And quotient is also 1. So we write 1 here and carry the quotient. Once again, we have 3 ones. So that will again become same. We write 1 here and carry 1 here. Since there is nothing in front of these values, we will assume these are 0. So what is it? 1, 0, 0. It's 1. Again, 1 remainder 2 is 1. And 1 divided by 2 is 0. So this is the final summation of this binary number. I hope this binary addition makes sense to all of you guys. This isn't much hard, but actually not very familiar. but it's very similar to what we did for the decimal number. So now let's move to the next step. Now that we have understand binary numbers, let's talk about bits themselves. So what is bit? Every single binary digit is called a bit. So if you see here, so let's say this is an binary number 1011. Okay. So every single digit, this, this, these are nothing but in computer terminology, these are called bits. Now there are two states of bits. Either it can be set or it can be unset. When a bit is set, what is its value? 1. When it's unset, it is called 0. So same terminology applies when we are updating its value. When we are setting, we are making the value 1. And when we are unsetting, we are making the value 0. So these are the two states of a bit. These terms are extremely common in interviews and low-level programming. So try to understand these bits. Okay, what is set bit? What is unset bit? Now, why is bits important? Because in every programming language, there are some data types, and that each of the data types are defined by some bits. Okay, so if you say one byte consists of 8 bits. Similarly, there is short, which consists of 16 bits. Similarly, there is int, this consists of 32 bits. Similarly, there is long, which consists of how many? 64 bits. Or sometimes you might also heard term like short is equal to 2 byte, int is equal to 4 byte, and long is equal to 8 byte. Now byte itself is equal to 8 bits, right? So these are the very common terms you might often hear during interviews or in any programming questions. Now, why is this bits important in any data type? This bits actually decides the ranges of value that we can represent. So each data type can have a range of number it can hold. If you can recall from our previous lecture, we have frequently discussed that integer cannot hold more than 2 to the power 31 minus 1, right? So that is because every data type is limited by the number of bits it have. So now before we discuss the ranges of each data type and how to calculate its range, we must learn another special thing in bit, and that is called most significant bit. So what is most significant bit? MSB stands for most significant. Most significant bits mean the leftmost bit of any binary number. Okay, the leftmost bit. So let's say if you have binary number like 10111 1. So let's make it 8 1 2 3 4 5 6 7 8. So this bit, which is lying in the leftmost side, this is called the most significant bit. Now this MSB is not just a random bit. This has some special meaning. It decides the sign of an integer number. It decides the sign of a binary number. Signs mean sign means whether it is a positive or negative. So it decides the sign. What are the sign? Either positive or negative. Also, this MSB is having the highest weight. So what is meant by highest weight is the positional value, the positional power of this is 0. This is 1, 2, 3, 4, 5, 6, 7. So the leftmost bit or the MSB is having the highest weight, right? Now, why are we discussing bit here? Why why are we discussing MSB or most significant bit here? Because so far, whatever we have learned for binary numbers, we did not know how to represent a binary number in negative form. Do we know this? No, right? If computer only understands 0 and 1, how does it understand whether a number is positive or negative? Can we do something like this? Can we reserve the MSB for deciding sign only? Can we do this for any binary number? Let's say if there is any binary number of n bits, can we reserve this always to decide whether this number is negative or positive? We can say like if this is 1, then this number is negative number, or if this is 0, this number is positive number. Can you do this? If you are thinking, yes, we can do this, you are wrong. Computer never does this. They never reserve any bit just to decide the sign of a binary number. So if you have learned anywhere, or if anyone have taught you this, that the MSB is reserved for deciding the sign only, that is completely false. Forget about that thing. Yes, it helps. It helps in deciding the sign, but it is not reserved. There is a difference. When I say it is reserved, what does that mean is if we have to assign some value, this bit will be never used, right? This is always wasted just to decide the sign. Only these bits will be used. So we are having a shortage of one bit. So that is not really necessary. There is one more disadvantage for just reserving the MSB for sign. First thing is wastage. Then the next thing is how will we represent 0? Now, since we reserving the first bit only for sign, if we have to write 0, we will have to write like 0, 0, right? Just to write 0 also, we will have to carry one extra bit just to decide the sign. Because 0 does not have any sign, right? It is neither positive nor negative. So 2, 0. Now, how will computer understand when it has to add two numbers? How will understand that the MSB is carrying the weight, will it just discard the MSB and then sum? No, right? It cannot do that. Now, just to do the addition, computer will require some additional information that, okay, this is MSB. We must not sum this. This will just for carry. We will not be able to add two numbers if the MSB is having the sign only, and it is only reserved for sign. We won't be able to this additions which we are doing so far. This will fail, and this will give incorrect result, right? So addition will give incorrect result. So that is why we never reserve the MSB for deciding sign only. That's why I told you, if everyone, if anyone has ever told you that the MSB is reserved for just deciding the sign of a binary number, that is completely incorrect, right? So this approach is incorrect, right? So then how do we decide the sign of a binary number or negative number? Well, when the first approach was failed using just assigning the MSB reserved for sign only, then came the idea of uh, one's complement. What it meant was, given any binary number, just invert it. So it will become like 0, 1, 1, 0, 1. This was one's complement. Okay. But again, it was later realized that this method is also not sufficient enough to represent a negative number. It was also having the exact same issues we were having when we were trying to reserve for the MSP. There was issue with two zeros, there was memory wastage, also there was problem in addition. Additional requirement was needed to perform the binary addition operations. That's why this approach also failed. Then later they introduced 2's complement. Now, what is 2's complement? First, you have to take any binary number, perform its ones complement, and then add 1 to it. Right? It was just an extension of ones complement, and then everything worked out of the box. So what it meant, first, perform ones complement, and then add 1 to it, and that will become 2's complement. This become powerful, and this solved all the problem which we were having here. Addition was same like before. There was no problem with two zeros and no wastage of memory because this was no longer reserved. Although this now, so basically let's first understand what is 2's complement, and then we will discuss all those things. So basically what it means was, let's say given any number, 10110, first perform one's complement. This will become 0, 1, 0, 0, 1, and then add 1. So when we add 1 to this number, it will become 0, 1, 0, 1, 0. Now this number is both signed as well as nothing is reserved. But how do we represent negative numbers with the 2's complement. So let's say you have number 4. So how do we represent 4? It is 1 0 0, right? Or let's say in 4 bits, how do we write it? It's written as 4 0 1 0 0. So first perform the ones complement. It will become 1 0 1 1, and then add 1 here. So this will become 1 1 0, and again 1 1 0, and then it become 1, and this is 1. So this is the negative representation of 4. So this is how we represent the negative number, or this is how we get the 2's complement. Now let's understand how negative number is being represented here. So basically, any number which is present at the MSB will be always treated as negative. Irrespective of whatever the bit is, MSB will be always treated as negative, not reserved. Whatever with the value there, it will be always treated as negative. So what does this mean? So let's try to convert this number into decimal and see how this thing is working. So here it is 1. So since this will be treated as 1 negative, we will take it -1 into 2 to the power 0 1 2 3 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 0 into 2 to the power 0. So if we sum this up, it's become -8 plus 4 plus 0 plus 0. So this become -4. So what was our original number here? It was 4, right? And now what is it? It's -4. So this is nothing but 2's complement. Now, the rule for 2's complement is always that to consider the MSB as the negative. Now you will say that how do we then represent positive number? It's very simple. When the first bit is 0, that will be a positive number. Why? Because you multiply anything with 0, that becomes 0, right? So again, if you do the conversion like this only, it will come out to be as 4 only. So if we do the conversion of this, applying the same rule as we did here, so the leftmost or MSB is always negative. So we'll multiply it with negative first into 0 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 0 into 2 to the power 0. If you sum this up, since this will be multiplied with 0, it will become 0. 2 plus 2 to the power 2, 4, 0, 0. This is 4. So see, this rule is not breaking the existing number, which is positive numbers, and it is successfully being applied to represent any negative number as well. So this is 2's complement, right? So once again, let's try to understand it with another example. So let's say we have number 9. So what is the binary representation of 9? So let's say we are representing this number in any of the data type which is having 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. So how can we represent 9 in binary number in 8 bits? 1, 0, 1, 1. Now all the things will be 0. We are representing in we are representing in 8 bits. Okay. Again, if you do the expansion like this, it will be 9. Now find the negative of 9. So what is the approach here? First step, ones complement. That means inversion of all the bits. So 1, 1, 1, 1, 0, 1, 0, 0. Second step is add 1. So if I add 1 here, so 1, 1, 1, 1, 0, 1, 0, 0. And if I add 1 here, this will become 1, 0, 1, 0, 1, 1, 1, 1. This. Now, once again, if I convert this into decimal using the conversion rule, so let's see, minus 1 into 1 into 2 to the power how much? 0, 1, 2, 3, 4, 5, 6, 7 plus 1 into 2 to the power 6 plus 1 into 2 to the power 5 plus 1 into 2 to the power 4 plus 0 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. This turns out to be 2 to the power 7 is 128. Now this is having a negative sign, so it will be 128 plus 2 to the power 6 is 64 plus 32 plus 16 plus 0 plus 4 plus 0 plus 1. If we sum this up, this will come as minus 9. You see, this is how we represent negative of any binary number using the form using 2's complement. I hope you understand how we did all this thing, how we applying the 2's complement. The rule is very simple. First, find the 1's complement. 1's complement is nothing but inversion of all the bits present in that number. If it is 0, invert it to 1. 1 to 0. And then once we have done that, just add 1. And whatever number you will get, that number is a negative of the original number. Right? So this is the way of representing a negative number in binary. Now, if you see, it's basically the same thing. The MSB is representing the negative weight, but it's not reserving. If you see, we are using it for calculation also. We are never discarding it. Even for the positive values also, we are using it. See, we are not discarding it. It is just that we are considering the MSB as always negative, and the same approach is being applied just with considering it negative number. So this was the 2's complement. Now, if we look at the previous problems which we had when we were trying to resolve the MSB just for decimal sign, wastage, now there is no wastage. There is no need to have two zeros to represent 0. We can just represent it with single 0. Addition will work as it was working previously. No extra hardware, no extra special instructions, right? So this is the power of MSB, right? Now we have discussed bits, MSB, binary addition, 2's complement, and now we know how to represent negative number in binary. If we have to find range, how to find range, or like for n bits, the range could be negative of 2 to the power n minus 1 up to 2 to the power n minus 1 minus 1. So this is the general formula for any number of bits. And applying this formula only, we used to discuss the maximum and minimum for integer. So for integer, what is the bits? We have 32 bits. If we apply the above formula, any number n can be from negative of 2 to the power 31 up to 2 to the power 31 minus 1. Right? Same formula can be applied to long, short, or any other data types. I hope you understood this range. How to find the range of any data type. First, we have to find the number of bits that data type can hold. Then, applying this formula, we can get the minimum and maximum value possible. Now you can think why we used to always talk about whether it will overflow integer or not in our previous examples, right? So this was the reason. Now we already discussed that in computer, everything is stored in binary only. So similarly, any text also is stored in binary. All the alphabets we know, like English alphabets like A, B, C, D, E, F, G, all these numbers are stored in integer format with some value. So all these numbers like alphabets A, B, C, all these numbers are represented with a specific integer number. Like this is represented with integer number 65, this is 66, this is 67, similarly up till Z. Similarly, we have small a, small b, those are also represented with some number. And this representation is called ASCII. So ASCII stands for American Standard Code for Information Interchange. Basically, in ASCII, you have all the numbers from 0 to 9, then all the uppercase alphabet A to Z, then all the lowercase alphabet small a to small z, and some specific and some special characters like dot, comma, question marks, like that, right? So originally, ASCII code was developed to store all these characters in 8 bits. So 8 bit can have maximum 128 values. So there was total 128 characters in ASCII. So I hope you guys enjoyed today's session and understood what is binary, how to perform addition in binary, how to find a negative number and how to represent negative numbers in binary, how to find the minimum and maximum range in a binary. In the next lecture, we will learn about bit manipulation and we will solve lots of interesting problems around that. So see you in the next lecture.